Okay. Can you hear me properly? I'll try and talk slowly. I just don't know how good the connection is. Okay. All right. So it's fine. Okay. So sorry, there have been problems. All right. Let's continue, and let's see if we can share properly. All right. That should have come through. Yeah. All right, so we were looking at linked lists, and we've been doing linked lists in the tutorials. We've been implementing a linked list in class as well. I think we got most of the functionality there. Let me just remind myself of what we got. So the focus really is on the singly linked lists. We'll look at the other variants of it as just simple variants. You won't need to be able to understand the code or do the code for the variants on the linked lists. As long as you understand the singly linked list, we're satisfied. You'll do more advanced node-based data structures in future years, so that's not a crisis. But where did we get to here? So we'll be able to insert at the beginning, insert at the end. I don't think we implemented all of those. We'll take a look. Certainly don't believe that we didn't do any removals. Did we even do insert first and insert last? Let's see. No, we hadn't actually implemented that. Insert first, we did do insert last though. All right, so we can take a look at those as we go along. But let's actually move through some of the theory. If you want to see implementations for insert first and insert last, if I don't get to do them now, you can see them in class. Sorry, in the tutorial for today, which not code blocks. Is available. So last is the code for those who are watching later, and we will continue. All right. So the linked list operations. So we've seen things for the default constructor. We've been implementing ourselves from first principles, so we might differ a bit from the ones in the nodes, but that's okay. Destroy list is very important. Traverse through all the elements in the linked list and free them as you move along. Did we implement one of those? Yes, we did. So basically the point is that you mustn't delete the node as you encounter it. You must first make sure that you're able to move forward before deleting the node that you've just encountered, because otherwise you won't have anything to follow. You'll have just deleted your only link. And then reset everything when you're done, which is exactly what we did. Initializing the list. So what does that actually mean, really? Like you can't pre-allocate space in the list because the linked lists grow and shrink by exactly the amount of data that they need to. So a linked list, that's one other advantage of a linked list. If you take, for example, a vector, it grows automatically, but it actually does so in a very greedy way. So most allocation patterns are what they call binary exponential patterns. So what that basically means is you allocate a capacity initially, you put stuff into the linked list, into the vector, let's say with pushback, and then when you reach the maximum capacity, so under the hood there's just an array inside the vector, it automatically allocates a new array that's twice the size of the original array, copies everything from the old array into the new array, and then deletes the old array, which means that for a large chunk of the time, you've got a lot of pre-allocated unused space in your vector. Whereas a linked list will literally only use the space it needs. As you add a new item, space is allocated for it. As you remove an item, space is deallocated. So it's much more responsive in terms of its memory usage. It doesn't dramatically allocate or deallocate stuff. Of course, there's a little bit of waste. For each node, there's that extra pointer. So if the data that you're storing size relative to the size of the pointer is very, very comparable, then it'll be inefficient because you're storing, let's say, almost twice the space that you need to. But if you're storing big things inside the linked list, then the relative amount used for the link to the next node is very tiny. All right, so printing and getting the length and retrieving data from the beginning or the end. We didn't have a dedicated function for that. We could have, I suppose. We could easily add that. But basically just returns the data front and last, or of head or tail, assuming that they're not empty. How you handle empty lists is also important. You can raise errors, like we did in the tutorial today. So we encountered a linked list, removing from an empty linked list. We threw an exception, or you could have it just have no effect. So if we wanted to add front and back, we could easily do that. So type T front. Put front value just so that it doesn't have the same name as. Oh, if we did it with begin and end, so it doesn't really matter. I mean, it's not going to clash because it's actually linked list colon or type T colon front and back, so it's not going to clash with any existing one. This is just an accessor, so it's not going to change any values. Okay, so we could implement our linked list, and we can decide how we're going to handle trying to retrieve a value from an empty linked list. I would say treat it as an error. So in that case, make a little family of exceptions, which I don't think we had at the moment, so we can easily add that. Just a little header file for our exception hierarchy. They're not going to really bother with any implementation details, so there's no need for a CPP file, but you could, of course, if you wanted to, add a CPP file. And then let's say, have a base exception class. Doesn't do anything. Ugh, not public. And then a base list exception. Kind of exception. Doesn't do anything. And then a retrieve from empty list is a kind of list exception. And then what we might want to do, simply bring in our exception hierarchy, and then when we hit this problem of, let's say, over here, what are we doing if we're trying to retrieve from an empty list? How do we know if our list is empty? We can check to see if head is equal to null, or we could check length is equal to 0, or we could check tail is equal to null, or we could check head is equal to tail is equal to null. That's also fine, but unnecessary. So if we're retrieving from an empty list, then we can throw a retrieve from empty list exception, and otherwise we will return heads value, which I think I call data. Check, yep. And pretty much the same story here. Back, except we will return tails data. And I think we had things that happened inside our linked list. Yeah, so now we can just add accessing values. I don't even remember what was in the front of object list. List dot front. Back of object list, retrieve back, and then let's just see if that works. Okay, that's correct, and then let's just make an empty list. Doesn't matter what it is. And let's try retrieve from it, and we should get the useful exception being thrown. We could put that in a try block and catch it nicely, or we could just leave it uncaught. Still gives us some information about exactly what went wrong, where you see there was a instance of retrieve from empty list exception. That's also why exception handling can be very nice. You get the name of the exception, which documents what's going on. That's why a lot of the time you don't really need to add extra detail if it's not necessary to your exception hierarchy. The kind of exception that got thrown tells you a lot about what went wrong. So that's fine. I'm not going to leave that there, but there we have it. All right, so let's carry on. Begin and end. We've spoken about iterators and we've implemented our iterators. So begin and end retrieve an iterator pointing to head for begin, and for the null that's after tail in end. I mean, obviously all nulls are actually the same null, but that's the convention. It does simplify some code, so we follow it. And then we will take a look at duplicating the list, which I do believe we implemented already for our copy constructor's sake. Yep, so duplicating our list is something we do. And insert last will handle the growing of the list, so not a problem. And destructor, copy constructor that make use of those, very straightforward. Assignment operator, pretty sure we did that, but you just check for self-assignment, free the list, copy the list, return yourself, good to go. And then what you can do and what we won't do here is you can extend linked lists by having basically two different kinds of lists, ordered and unordered lists, where you either preserve or don't preserve the order and use inheritance to keep track of that. The thing that gets affected there is basically what happens when you do things like insert first and insert last, because you can't specify where something must go with an ordered list. It must go in the correct position. So you could basically implement insert first and insert last as virtual functions and then override them so that they always search through the list through a traversal, find the correct location, so that's where the predecessor's value was less than you, less than or equal to you, and the successor's value was greater than or equal to you, and then insert at that location. So it's you can't give free access to insertion and at an arbitrary point. So that's one possibility. So yeah, basic insert first, basic insert last, and then let's take a look at deletion. So removal from the back and front of the list. I did that quite comprehensively in my tutorial today, but we can take a look here. Let's do the easiest implementation, which is removal from the beginning of the list. So let's take a look. So if we wanted to remove from the beginning of the list, that would be a void function. So let's call it remove from front. And then we have to think about what the possible scenarios are. So if we look at that, what are our scenarios? Well, one scenario is that the list is empty. We'll treat that straight up as an error. Other scenarios are that the list is consisting of only one node. So what does that mean? It means we've got head and it means we've got tail, and they're both pointing to this single solitary node, which is pointing to null. So that's not difficult. And the other case is then where there's more than one. Doesn't matter whether it's 2 or 3 or 4, but you've got a sequence of nodes, and head will be pointing to the first of them, and tail will be pointing to the last of them, and they will be linked to each other in sequence, with obviously the last one pointing to null. So as I said, truly empty list, that's an error, removing for it. List with only one node, that's easy enough. What do we need to do? Well, we just need to delete this node and set both head and tail equal to null. So let's just do it visually. Delete the node. Set head and tail equal to null. And then no matter what we do, we're always going to decrement our length. So let's check that this works. And then check that it works. Okay, we'll do insert first in a moment as well. So we're removing from the front of the list. What do we need? Handle our three cases. So first case, list is empty. Check that by seeing is the head equal to null. If so, throw an error. What errors did we have? We had retrieve from empty, so let's have remove from empty. Which is also a list exception. And we can throw that, remove from empty list. Problem, now we've got the case where the list has got a single value in it. We've got a length, so we may as well just check to see is length equal to 1. So that's list has one node. Then what did we say we needed to do? We said we needed to delete that node, set head and tail equal to null. And at the end of the day, no matter what happens, we are going to decrement length. Empty will never get there because of throwing it, and if it's anything else, it'll drop to 1 less, including 0. So here we go. So we simply delete the node that is being pointed to by either head or tail. They pointed to the same node. And then we can set head equal to tail equal to null. And that's the simplest case. Now, if we've got the slightly more sophisticated case over here, where there's multiple nodes, but it's really not that complicated, all we need to do is to be very careful. First things first, we want to make sure that we don't lose the entirety of the list. So we can't just delete this straight away, because then head's pointing to a node that's no longer there, and everything is broken after that point. So what we want to do is we want to get the second node, whatever that might be, then delete the first and make head equal to the second node. So let's handle that case. So this is the case where there's multiple nodes, and we want the second node. So let's make a little pointer to grab hold of it. The successor of head. This could wind up being tail, which is not a problem either. Then we can delete the old head, and we can set head now equal to second, and move everything along. So let's test this. So we've got our front and back functions. We can use them. So let's actually go for obj list and remove front. Interesting that that's not completing, but let's just see. And then print the list and see if the front was removed. Okay, didn't like that. Why didn't it like that? I called it remove front. Oh, I put it in the iterator. That would explain it. Not inside the list itself. My bad. Again. Okay, and we can see that the node at the front of the list was removed. And obviously, if we just make a simple little list that's only got one thing in it, so we can test that case as well. remove it. And then print. And you should see that adapt automatically, unless we have an error. Okay, I'm not really seeing, because we don't really say that we're going to be printing it, so we can just say removed only node, and then there'll be nothing after that. So there we have removal from the front. Removal from the back is actually a bit trickier. So take a look at that. The tail. So we've got three cases again. We've got the empty case, which is an error. We've got the case of 1, which is exactly the same as the case of 1 from removing from the front. Then we've got the case of multiples, where we have to do something a little bit trickier. We can't just delete tail, because then we're going to lose tail, which is a problem. It's going to be pointing to nothing. We want to make sure the tail winds up being updated and pointing to the previous node. The previous node, second to last node, we have to get that node. These links only go in one direction, so we have to basically loop from the head until we get to the second last node, which is going to be the one that points to the current tail. Once we've got the second last node, so let's call that S, and tail, then we can safely delete tail, set the successor of S to null, and set tail to point to S. So let's just do that visually. So delete this, goodbye, make the successor of nail, the successor of the second last one, which will be the new tail, point to null, and update tail so that it's the new tail. So that should be fairly straightforward. Let's give it a whirl. It's a little bit more complicated than removing from the front. Then is removing from the back. So void remove last, and do that. List. And then the three cases. So simplest case, list is empty, throw an error, still a removal from empty list error. List has one node in it, same logic. Head and tail need to be updated. At the end of the day, whatever is going on, we still need to decrement length. And then the only bit that becomes more complicated is the multiple nodes case. So what did we need to do? We needed to find the second last node. And then once we've got that, we can safely process the list. So let's make a little node pointer, our second to last node. Started off at the head. Traversal, but we're not going to traverse all the way until we hit null, because what's the point? Then we can't delete anything. We're going to traverse until we find the node that points to, or whose successor is the tail. So while second to last the successor is not equal to the tail, keep going. So keep going, let's not forget that. Node second last is equal to second last next. And then we should eventually hit that. And so if we do, we've now got the node pointing before tail, and we've got tail itself, so we can safely delete tail. Node second to last points to null. It's going to be the new tail. Tails always point to null. And then we can set tail to be equal to this temporary node. we should have removed an arbitrary node. So let's test this. So all right, so let's just keep working with object list. So let's say we're going to remove last node, and so we say object list remove last, and then let's print it. Already tested the empty case and the case with 1, so we just need to test the complex case, which is the case with multiple, and let's see where we get to. And we can see that Z has been removed from our list. A was removed earlier, and we've just removed Z over there. So let's see if there's any questions at the moment. Okay. You know, I understand your point. Like when you first use a vector as a programmer, you're like, wow, this is amazing. It grows and shrinks, or it doesn't shrink automatically, but it grows automatically. You could erase values from it, and then you know, it might shrink down, but certainly grows for you. But yeah, and then you realize just how aggressively it does that. Is that necessarily what you want? Well, it depends. For speed's sake, that actually can be very effective because it reduces the number of allocations that need to happen and the number of copies that need to happen. But from a memory usage point of view, it's less effective. So it's always a trade-off between space and speed. Yeah, I would say that in that sense, linked lists are more dynamic because they literally only grow as you need them. Okay, this is a great question. So begin gives you an iterator back. Begin gives you an iterator back and end gives you an iterator back, while front and back give you the values at that location. So remember, the iterators were those smart pointers we created, whose purpose was to give you access to everything over here. So they implemented the dereferencing, unary, asterisk operator, incrementing, and comparison and assignment, and you could use them to move through the list. And we did that over here with this loop, where we got the iterator to the beginning. As long as we hadn't reached the iterator to the end, move forward, dereference, do whatever it is you need to do. Whereas front and back just give you a copy of the value that's at the beginning or the end of the linked list. So very good question. Yeah, so perfect answer. So it'll be next week. Next week. When already available, been available since the day after the main test. You'll receive confirmation on Friday if you were successful. I mean, if you've submitted the form, it's there. It's a Google form, but you'll receive confirmation as to whether you were approved on Friday. All right. Cool. All right, so let's take a look and see where we're at. So yeah, so deletion of nodes. Deletion of arbitrary nodes is kind of useful and important. So let's see. Now, we might do more of that going forward. I don't want to spend too much time now implementing every single function. This is one that is worth looking at. So if I don't do it now, I'll make sure that we do it before the end, because deletion from an arbitrary point is kind of important. I'll go through the basic idea with you, that I have already before. The idea is that if you want to delete something in the linked list, if it's the beginning, it's easy. If it's the end, it's easy. When it's a little tricky. You make its predecessor link to its successor, then you can safely delete it. So there you go. They link around it and then delete it. And then insertion, we've spoken about those different cases as well. Okay, these are arbitrary insertions. So insertion at the beginning, not too difficult. Insertion at the end, not too difficult. Insertion at an arbitrary point, a little bit trickier. Create the new node. Make sure that it links to the node it's going to be coming before. Then make that, or if you've got the node that is you can make that node point to it. You can make it point to the successor of that node. So you must save the extra link in a pointer, and then basically link it in. So it joins here, assign it. If you do the right order, you don't have to save it. So you create the node there. Let's draw a picture rather. So let's say we wanted to insert a node over here inside this linked list we've been working with in our pictures. Okay, we don't need a second lost, that's already done. So let's say we wanted to add a few more nodes. Okay, let's say we wanted to add a node inside the list. Over here, we would need to make sure that we point to the successor of the linked list, so the successor of the node we're adding after, and then make sure that that node points to us, and then we've been introduced. So then this link is gone, and we are the new node in the sequence. All right, so I just want to quickly see how much time do we have left. What time does this